let's try to record it. So we minimize it. Okay, now this is our lecture 3. This is lecture 3, and this one topic we'll read here, that is the mathematical tool for studying random process. Mathematical tool for studying random process. So in earlier chapter we have seen that what is the meaning of random process, and we have seen that the speciality of random process is that sometimes each waveform, which we say is that the sample realization can be deterministic, but the process is probabilistic in the sense that we don't know which deterministic waveform will come. So we don't know a priori which waveform will be generated, because the generation of the waveform will be a probabilistic and it will come from the outcome of an experiment. So we can write, so we have seen that in many cases, in many random processes, each waveform, that means each sample realization can be deterministic. But the process is not, in the sense that which deterministic waveform will come, we don't know. Now the question is how to characterize. We don't know a priori. Now the question is how to characterize a random process. So this is a big question. So how to characterize a random process? So, or how to describe a random process? Because we need to describe it with some mathematical form. So let's say what we see, random process means a sample realization and ensemble of sample realization, right? Random process means, so this is t and this is xt, rather x1t. We have another realization, could be t versus x2t, and we have several other realization, and ultimately we might have, say, xnt realization, something like this. So now let's say we want to describe the process. How we can describe the process? So first you have to understand that we will do it over the ensemble. Ensemble is important. Let's say we took a time t1. And we see what is the value of x. So at t1 this is the value. So this is x1 t1. This is t1 again. In t1 we have the value x2 t1. Similarly at t1 we have the value xn t1. So all together will form a population at time t1. Again similarly we took, say, time t2, we have x1 t2, t2 we have x2 t2, at time t2 we have xn t2. All combined together forms an population. Okay, so we call this population as x of t1, we call this population as x of t2, so and so on. So this way it forms the, so this is the difference between the deterministic process and random process approach. In random process we see over the ensemble, and then let's see how. So at t1 we get the different values of xt1, x2 t1, x3 t1, like that, and together, combined together, it becomes an ensemble and it becomes a population. Now let's see. Just a minute. Okay, so now, so let us describe then. So we have time, so like this, t1 maybe t2 is greater than t1, t3, and so on. We have tl, l is any arbitrary integer. So now we are trying to deal with a, so now we have the L number of population, and we try to find out the joint distribution of the random variables. So we are like to find out or describe the joint distribution let's find out or describe the joint distribution of xt1, xt2. We have described what is xt1, and joint distribution of all this xtl. So we say that if we know the joint distribution, or we could say that if we know the joint probability distribution function, joint probability distribution function, if we know the joint probability distribution function PDF, if we know the joint PDF, we say that we can describe or characterize the random process. So how we can describe a random process? We can describe a random process if we know the joint distribution over the ensemble. So to describe or characterize a random process, we need to describe joint PDF. What is that? Joint PDF. What is this? Is f of x t1, x t2 x tl of x1, x2, x3 xl. So So need to determine the joint PDF, this one, for all L and for all T1, T2, TL. So if we can describe this joint PDF, that means we can describe the random process. Now you see that the description of this is a very cumbersome, because we need to know any joint distribution among the any number of time population. So that is very cumbersome. So it is obvious that such description of random process is very cumbersome and extremely difficult or impossible to do so. Okay, so it is obvious that such description is very cumbersome, because at any number of point of time we need a joint distribution. That is a very cumbersome description and extremely difficult, and it is impossible also. Fortunately, the most widely used random process model have specific structure that permits the computation of soft statistical specification. So there are a few things. So first thing is that most widely used random process random process models or random process, most widely used random process have special structure that allow to determine or express such joint PDF. They have a special structure that determine or express the joint PDF. Next thing is that if we do with linear system, which we will be doing in this book, which we shall be doing, if we do with linear system or process the random process with linear system, we often do so by considering the first and second moment, and we process only the two moments with linear system. Okay, so if we deal with linear system, which we will be doing in this book, or process the random process with the linear system, we often do so by considering only the first and second moments. That means we describe the random process. So we describe the random process. We describe the random process with first two moments, and we would like to know the first two moments of the output. So that makes our life much simple and easier. So we'll describe those two moments now. So that makes our life easy. So what are these two moments now that we'll describe? The first thing is mean. What does it mean? What is the mean? So the first thing is mean. So mean means average. What is that? So mean, you can say mean equals to mu x. So mean equals to mu x t I, or rather we can say mu x t I, because I is, we can take 1 2 3 4, and mu x is average mean over the ensemble. So mean, so I emphasize it is the mean over the ensemble at time ti. So what is the mu? That is equals to e of x ti. So xti is a ensemble, so e of xti. Right? Now if we have so this is the mean function. So simply it is the expected value of the process. So if we know the distribution, so for a continuous system, if we know the distribution, if we know the distribution, we can tell the mean will be the x into that distribution. So if we know the distribution, then we can write mu x ti will be equals to e of x ti will be equals to minus infinity to plus infinity small x fx, okay, of small x comma ti dx. Okay, so x of, I should write x of ti dx. Okay, so, or rather I can write x of x dx. So for a discrete system, we could write mu x of n, or rather I should write ni, equals to expectation of x in I will be equals to minus infinity to plus infinity x f of x in I small x dx. So this is over the ensemble. So So over the time, in many cases, of random process, over time the mean may change. Over time the mean may change, or it may not change. It depends on the random process. Now if we want to take some example, let's say, so first characterization is mean. Okay, this is a first order moment. So if we take one example, so let's say example, let's say we consider a random process, or rather a discrete random process, or let's say first continuous. So we continuously take. So let's see, the xt is a random process of a sine omega t, where a is from uniform distribution of 0, 1. Okay. So what does it mean? It means a will be something, another ensemble could be like this, another ensemble could be like this, like so on. Okay, t versus x. So then what will be? So we have to take the average at the over the time. So let's say what it will be. It will be, let's say, expectation mu x. So let's say mu x t will be equals to e of xt will be equals to, at any time t, e of e sine omega t will be equals to e of a into e of sine omega t. E of sine omega t will be time omega t because it is over the ensemble. So e of a will be the 0 to 1, so it will be 0.5 because it is a uniform distribution, 0.5. E of sine omega t will be sine omega t, so it will be 0.5 sine omega t. So mu x of t will be 0.5 sine omega t. So it's a function of t, it's not a constant. Okay. So now another example, let's say discrete case. So let's say a discrete random process is defined as, Bernoulli's a discrete random process is defined with Bernoulli's distribution with the probability of xt equals to 1, that will be half minus half of e to the power minus lambda t. Okay, and the probability will be 0, so xt can be 1 or 0, probability will be 0, will be the rest of the thing. So now the mean function, what will be the mean? So mean value will be mean value will be okay, sorry, this is not a discrete, this is a continuous case. So mean value of this mu xt will be equals to e of xt will be equals to 1 into probability of xt will be equals to 1 plus 0 into probability of xt will be equals to 0. This will be 0, so we should not take anything. So this is 1, that means equals to half minus half of e to the power minus lambda t. So that's it. This is the mu x. Okay. Now the second thing, this is a first order moment. Now another thing we need to define, which is a second order moment, and we call it a autocorrelation function. Let's define it. This is also very important. So autocorrelation function. So autocorrelation function just 1 minute. So autocorrelation function can be defined. What is autocorrelation function? Autocorrelation function is r of x ti comma tj will be equals to e of xti to xtj. Okay, so this is the, so at some point ti all population, at another point tj all population, and expectation over that. So over the ensemble this is kind of I, over the ensemble this is kind of j, and then this is a ti and tj. So this is time, and we will get all xti and tj, and then we will do the multiplication at each time, at each sample realization, and we will get some number, and we will take the average of it. So ultimately we will get a single number rxx, which will be a function of time. So now, so this is the simple thing. Now if we know, so earlier we see that we need to know a single PDF at some point of time ti. Now we need a joint PDF of some time ti and tj. We need a joint PDF of some time ti and tj. So let's write. So joint PDF at some time ti and tj is f of xti xtj. Okay, xti and xtj, and x1 x2, because these are the two variables. No, just 1 minute. We are describing xt1 xt2 x1 x2. Okay, so we describe the autocorrelation function as xt1 and xtj, x1 x2, that way we are going to define. Just 1 minute. Yes, so this one is this. So now, so what will be the rxx? So rxx ti comma tj will be equals to the second order moment. So double integration minus infinity to plus infinity x1 x2 f of x ti x tj x1 x2 dx1 dx2. So this will be the double moment. And then for a discrete system, means that in, okay, so time is discrete. For a discrete system, rxx in I in j will be equals to expectation of x in 1 and x in 2 will be equals to minus infinity to plus infinity x1 x2 f of x1 in I in j x1 of ni x of ni, one will not come, x of nj ni nj, then x1 x2, then dx1 dx2. This will be the whole point. So obviously the autocorrelation describe the relationship between two ensemble sample. So it is a 2 between the two set of ensemble sample. Okay. So now very frequently what we used to do, say let's say we are doing is Ti and Tj, and we generally call that Tj minus Ti will be equals to tau, and we call very frequently Rxx Ti comma Tj will be equals to, we call it Rxx Ti comma Ti plus tau will be equals to Ti plus tau will be equals to E of x Ti and x Ti plus tau. Equal it. Okay, now example. So one thing I must emphasize, why this is auto, because you see that why it is auto, because you see that the relationship between the same process, we are taking the same process x, same random process x. So the word auto, sometimes we call auto dash correlation, sometimes together we write. So the term auto refers to the fact that both the samples in the correlation function or the covariance function come from both the sample come from the same process. That is why auto, same process. Okay, let's say give some example. So example is, let's say xt, previous example, xt equals to a sine omega t is from uniform distribution of 0 1 0 1. A is from uniform distribution of 0 1, and then what will be our xx. So solution, rxx t1 ti comma ti plus tj will be equals to e of xti to xtj will be equals to e of xti is a sine omega ti to a sine omega tj. It will be equals to e of this. So e of a square sine omega ti sine omega tj, that will be equals to, what will be e of a square? So this is uniform distribution 0 and 1, so a square will, all the square you have to do. So it will be 1 by 3. Sine omega ti sine omega tj. We can write easily 1 by 3 sine omega t sine omega t I, or it can be t, anything, t minus t plus lambda. Okay. Now another thing is remaining, which is the autocovariance function. Again, auto comes because the sample comes from the same process. So autocovariance function. So what is autocovariance? Autocovariance is cxx ti comma tj will be equals to e of xti minus mu x ti to x tj minus mu x tj, this one. Okay, it can be easily proved that. So if we that will be equals to e of xti to xtj minus mu x ti into e of x tj this minus mu x tj of e of x ti plus e of mu x ti into mu x tj will be equals to e of x tj. This is rxx, we know rxx ti comma tj. This one mu x ti, mu x tj, and mu x ti both will cancel out. Look at this. This is mu x ti, mu x ti. Just 1 minute. This should be plus, yes, plus this you will go out mu x, it should be plus or minus, just 1 minute. Sorry, it will not cancel. This is the problem. This will be 2 minus 2 mu x ti to mu x tj plus mu x ti mu x tj. So this will be equals to rxx ti comma tj minus mu x ti mu x tj. Okay. Okay, in the next class we will do the cross correlation or cross covariance. So that is the next class. Let's stop here. Next class we will go with the cross correlation and cross covariance. So now we read the auto. Okay, thank you.